Our project is to parallelize finite element method for 2D shallow water equations. Shallow water equations are simplified Navier-Stokes equations, which are often used to model various kinds of waves in ocean or atmosphere. It's also used to model tsunami. The purpose of our project is to speed up the discontinuous Gherkin finite element method for shallow water equations in Python. The first thing we did is to figure out bottlenecks in our serial code. It turns out that the matrix assembly and the linear sparse solver takes up most of the time. Then we proceed to parallelize our algorithms. There are two approaches to take. First, we tried CUDA.
At first, we prefer to use cusp to perform matrix vector multiplication and solver. We didn't successfully bind it with Python, so we began to write the kernel by hand. Our multiplication kernel performs better when the sparsity is comparably large. However, under our problem, our kernel doesn't beat the built-in function. We use the GMRES to write the solver kernel. Our kernel is slower than the built-in function, so we came back to the Python library at last.
Then we turn to MPI. First, we partition the mesh so that each process owns a subset of matrix to enable local assembly. It's easy to assemble diagonal matrix, but it's much harder to assemble non-diagonal matrices because they need information from their neighbors. We compare the time for serial and different number of processes with different mesh resolutions. When we increase the mesh resolution to 0.1, using 6 processes achieves 5 times speedup. Next, we continue to parallelize our linear solver. This includes 2 parts. The first part includes a lot of sparse matrix vector multiplications, and the second part is sparse linear solver itself. After matrix assembly, instead of computing matrix vector multiplication on process 0, each process is responsible for doing its own multiplication. If we look at mesh resolution of 0.1, 6 processes is around 3 times faster than the serial.
From the final result, we can see the optimal speedup is achieved with 6 processors. This is because more processors cost more communication time. What's more important, the speedup and efficiency increase with smaller mesh resolutions, which means our algorithm is efficient in handling complex physical problems. Our project is a success. We achieved 4 times speedup in the most time-consuming part. We will finish the CUDA kernel and apply it on a larger scale problem, such as the 3D Navier-Stokes function.